So, hi everyone. Welcome to my talk on Etna, an evaluation platform for property-based testing. So, before going into the details of Etna, let's start briefly with what property-based testing is, right? So, let's assume that you want to write a binary search tree because we all love binary search trees and we write them all the time. What you do is you first define your type, and then you define your invariant, and then you start writing your functions, right? Such as insert. And at this point, you start to question, okay, how can I make sure that my code is correct? And you want to test that. And one such option that you can use here is property-based testing. In property-based testing, what you do is you write these executable specifications that define the correctness of your program with respect to some properties. And here what we have is, if you have a valid binary search tree, if you insert any key to that, the resulting tree should still be a binary search tree, right? And once you have these types of properties, the next thing you're supposed to do is you want to generate inputs to them so you can test those properties and make sure that your code is correct. So how do you test how do you generate these inputs? You could write something by hand, but the better option is to use a framework or a library like QuickCheck. QuickCheck is the most popular option around. It's been around for more than 20 years. But is it the only option? Of course not. We can have small check, like we have frameworks like small check and lazy search that does enumeration-based input generation. Or we have methods such as combinatorial testing that generates inputs in smart and fancy ways. And are you limited to Haskell? Does property-based testing only exist in Haskell? Of course not. If you go into Cogland, for example, you can have QuickCheck or FastCheck. So you have plenty of options that are not even shown in this graph. And what do you do at this point? You want to make some choice, right? You want to choose one of these things. And we are all scientists here, so we want to make informed decisions based on data, right? And aren't these frameworks quantitatively evaluated? Don't we have data on them? Of course we do. We have plenty. So in this graph here, what it shows us is again a subset of all things available. But the colored blobs you see in the middle are some case studies that these methods on the outer edge were evaluated on. And what is the problem here? So the problem here is that when you have two different methods that share one common case study, that share one common quantitative analysis, then you can talk about them in terms of their performance in that common benchmark, right? You can make your decision based on the data, on those common case studies. But if you're talking about two frameworks or methods, such as QuickCheck and SmallCheck in this graph, that do not have any evaluations in common, then it would not be possible to talk to them in terms that depend on data. So we wouldn't be able to make informed choices on them. And that is the problem that we're talking about today. Within the property-based testing space, with all of the abundance of methods and case studies, the problem is their ad hoc nature, the fact that they are unstandardized, the fact that they are not always comparable, the fact that they are not compatible. So to overcome this problem, we have worked on Etna. Etna is a multi-language, extensible evaluation and analysis platform that we have populated with a set of workloads, programs that you can test your testing tools on, that come from areas that functional programming is heavily used, and that existed in the literature before. We have also added some baseline strategies that if you are a property-based testing tool developer, you can evaluate your own neo-fancy generation strategies against those baselines. We have added some example experiments that we have done on Etna in the process of developing it, and to guide you into showing how you can use Etna, and also to demonstrate the usefulness of Etna in a different number of cases for different objectives. And at last, we have added some built-in analysis and presentation methods into Etna, so that once you have done your evaluations, you can write your papers easily. So, for the rest of this talk, I have two main agendas, and the first one is introducing Etna to you with the details that you're going to find useful if you ever want to use Etna. And in the second part of the talk, I will talk about our experiments with Etna, and I will try to demonstrate how Etna can be useful to you in a different number of cases, if you are interested in property-based testing. So let's go into the details of Etna. The first part of the details I'll talk about is about evaluation. So how do we evaluate testing strategies within Etna? And here we use mutation testing. So you might be asking what mutation testing is. Let me briefly explain to you. Let's go back to the binary search tree example at the beginning. And here is the body of the insert function. So insertion function consecutively compares keys of the item with the keys of the nodes in the tree, and it finds the right place of an item within the tree, right? And consider this version of the same insert function where we have a bug. If we have two keys that are, like if we have an item that already exists in the tree, then instead of replacing the value of the item, we are just going to add a new item with the same key, which is a bug. And if you have a good testing methodology, if you have a good tester, you would want it to find a bug like this, right? And that is what mutation testing relies on. Mutation testing relies on the fact that if you mutate a part of a program to incur a bug, and then you can run your tester on it, you can run your testing methodology on it, and looking at its performance, if your mutants are realistic enough, if they are close to the, if the testers, testing methodology's performance on the mutant reflects its performance in real world, then you can run realistic evaluations of your testing methodology, right? And that is what we do in Etna. In Etna, we rely on handcrafted mutants that come from different studies in the past, such as how to specify it, and we add them to our workloads using this comment-oriented syntax. And I have talked about workloads, so let's go into what they are. So a workload in Etna is a program with some set of properties, like the binary search tree with the insert valid property we had, and some set of mutants, as the one I have shown before, like insert GT. And within Etna, we have three categories, like today, we have three categories of workloads that come from areas where functional programming is heavily used, and property-based testing tools have been evaluated in the past. The first is data structures, where we have red-black trees and binary search trees that have many properties that come from, as I said, how to specify it. The second is languages, where we have simply typed lambda calculus and system F that have progress and preservation as properties. And the last one is coming from the security domain, the information flow control with non-interference property. So with all of these properties, and what happens when you actually run Etna? Let's say that you decided to use it, and you have some new fancy generation strategy, and you run it on one of these workloads that I mentioned. What do you see at the end? So here's our bucket chart. I see a lot of numbers here. Let's demystify it a bit. So here we see that we have 36 tasks that are mentioned, like that this bucket chart refers to. So let's pause for a second and talk about what a task is. So when you have some properties and some mutants, not all mutants are going to be triggering all of the, not all mutants are going to be incurring bugs in all of the properties. So what I might mean by this, if we think back about the binary search tree example at the beginning and the insert valid property, if we mutate some part of the delete function, that property is not going to be invalidated, right? So when you have X number of mutants and Y number of properties, the total number of tasks is not X times Y. You have to think about which of these pairs actually incur bugs. So which of them are tasks. So here we have some imaginary workload with 36 tasks. So your tester is supposed to find all of them, if it's good enough. And what does the dark to what does the black to white gradient mean? So here, what we have is your testing methodology, when it was evaluated on this workload with 36 tasks, it was able to find 14 of these tasks within 0.1 seconds, and it was able to find 6 of them under 1 second, and it was unable to find bugs for the 4 of the tasks within the 60-second timeout that we had. So we have talked about what workloads are in Etna and how you can see your results. So what can you actually do with Etna? What are the use cases that the platform provides you with? And the first is you can run the existing experiments in Etna today instantaneously without any effort, so that you can replicate all of our results from the paper. And you can also add new experiments on top using the existing testing strategies and workloads. So if you're curious about any question about in property-based testing, and you think that you can answer those questions using the existing by evaluating existing strategies on existing workloads, you can use that. You can also add new strategies. So if you have a new fancy generation technique, then you can add that to Etna by complying with some simple language level conventions and run your own new generation strategy against the baseline strategies that we have provided you with. So you can benchmark it. You can add new workloads. If you think that you have a program that is going to help Etna be more representative, you can add those workloads so that the rest of the community also benefits from them. And at last, if your favorite language is not Haskell or Cog, so you want to do property-based testing in a different language, you can add a new language driver that's going to allow us or other people to add new strategies and workloads or also run experiments. So let's go into the second part of the talk, where I talk about the experiments that we have done with Etna. So we have 5 experiments in Etna today that we have reported in our experience report. And I would like to talk about these experiments in 2 phases. And the first one is the first 2 experiments about comparing frameworks in Haskell and comparing generation strategies in QuickCheck in Cog. So the reason I would like to have these as one group to talk about is that the existence of these experiments already fill some of the blanks that we have talked about at the beginning of the talk in the circuit diagram. And the second phase is we have 3 more experiments, and these experiments they originated from our questions that we are curious to answer in terms of property-based testing. So these experiments both showcase that Etna is not only useful for comparisons between tools, but it can also be used for a variety of experimentations for different aims or objectives. And they also guide, they're also aimed at guiding you in creating your own experiments within such different settings. So let's go into the experiments. The first experiment we have is comparing frameworks in Haskell. So here we have 3 three frameworks and four generators. The two of the generators come from QuickCheck. One is the naive type-based generator that is automatically derived from the type information in Haskell. And the other one is the bespoke QuickCheck generator that we have written by hand. And the bespoke QuickCheck generator is aimed at being a top line that automated methods should aspire to achieve. And the other two are the lean check and small check generators that are both enumeration-based generation techniques. So let's see how these different generators fare in our workloads. When we look at the binary search tree workload and how the methods fare, we see that both quick check and lean check are very close to our bespoke generator, the top line, and small check falls behind them. And when we go into the red flag tree, we see a similar trend with respect to ordering going in the same way, but we see a drop in all three type-based methods. So let's pause for a brief second and investigate, talk about why that is. So going back to the property example at the beginning and looking at the precondition of the property, where we have, if the original tree is a binary search tree, then the result should be a binary search tree. So if our testing strategy is not able to generate a valid binary search tree, then we really cannot test this property. And in cases such as red flag tree, as the invariants of a data structure get more and more complex, so it becomes more separate from the type definition itself, it becomes harder for a type-based generator to satisfy the preconditions. So we see a drop in all three of the type-based generators, but we still see the same ordering between them. And when we look at the whole picture, so all four experiments all four workloads in Haskell, we see the same trend continuing. And one major key takeaway that one could have here is that if you're today using small check, it is definitely worth checking out lean check as far as our experiments go. So now let's look at our second experiment, that is comparing different strategies within quick check and COG. So here we have four different generators, all written in quick check. And the first one is a type-based generator, similar to the Haskell one. And the second one is a type-based fuzzer that merges property-based testing with AFL-style fuzzing. The third is a specification-based generator that is automatically driven from the inductive specifications in COG that are similar to the invariants that we have seen, such as the ISBSD. And the last one is a bespoke generator that again acts as a top line. And we see that all of them are very performant in our binary search tree example, like binary search tree workload. And we see a similar drop in performances in red flag tree. Here we can see that specification-based specification-based generator is rather better than the type-based ones. And again, looking at the whole picture, although we see a similar trend, we have two twists here, and they're both in IFC. So the first thing we see is that there is no specification-based generator for IFC. And the reason for that is IFC doesn't have this one inductive specification that defines its validity as a precondition. And the second is, although the type-based fuzzer it is less performant than the type-based generator in all of the other workloads, it solves 7 tasks in IFC, whereas the generator solves none. And the conclusion that we can draw here is that even though fuzzing may not really may not be worthy in all of the cases, in cases where the generator is not able to satisfy the preconditions, the fact that fuzzing has some feedback may allow it to solve some of the problems. And our third experiment is about exploring the effect of size in bug finding. So there is this folk knowledge that if you have a larger structure, then the existence of an exponential number of substructures in that is going to mean that it can act as if multiple inputs are being tested at the same time. So is this always correct? We wondered. And we decided to answer that by designing this trial and running it in Etna. And here, the generator is configured with generating different sizes of tree, and we look at its performance in finding bugs. And what we see here is that even though it's mostly correct, in cases where you have dependencies between different inputs, it may become harder if you have larger structures. And let's just stop for a second here and think about what this means. Is here when you have two keys, and the bug exists only when the two keys are the same, right? So if you're sampling a very large space, it might become harder for the two keys to be same. But if it's a smaller space, then the probability of collision is higher. So in cases such as this, where there are dependencies between multiple inputs, the fact that the input space is greater or bigger can mean that the bug finding performance drops. So let's go to the last experiment that I will be reporting on today. That is, as we were running the comparisons in Quick Check, we have realized that the type-based fuzzer has been performing worse than what we would expect it to. So we started investigating in what the reason for that could be, and we have realized 2 points in fuzz check that we could have improved, and we have used Etna to compare the old version of fuzz check with the new version, and have seen dramatic improvements in its performance. So with this experiment, I'll be completing my talk. And if you are interested in Etna, what it can do, and what it's about, you can definitely check out the paper. But I would strongly suggest you to just come use it with us. Just talk to us, reach to us, so we can work on onboarding you, and it can be more helpful to the community because we have built Etna for you. Thank you.
Thanks, and we've time for some questions. Actually, before I ask any particular questions, I just want to say thanks. I've done some work in the past in property-based testing for OCaml, and one of the real problems with it was that it's very hard, or it was before this work, very hard to evaluate whether you're winning. You do something, it finds some bugs, and trying to decide whether it is better or worse than the last thing that tried to find bugs is very hard with no standard benchmark suite. So thank you for causing this to exist.
Thank you.
But the question I wanted to actually ask, though, is you mentioned the possibility of adding support for new languages. How much work is that? Should we implement all the benchmarks, or what's the...
So what happens is, so all of this is incremental, of course. So they're orthogonal, right? Like adding a new strategy or adding a new workload, they're orthogonal works. The base work that you're supposed to do is, when you have a program, you need to be able to build it. You need to be able to apply mutants to it, and you need to be able to run trials on it, right? So if you implement these methods that are required for running experiments, then you can just start adding new workloads or strategies in an incremental effort. So it is some effort, and it wouldn't happen overnight, but it's not impossible.
Okay, thank you. Yeah.
Hi there. So I wanted to ask, first of all, you included small check in your evaluation. Was that the strict or the lazy version?
So I think it's, yeah. In these experiments, the performance difference was negligible.
Okay. So very often the lazy version outperforms the strict version by orders of magnitude.
Let's take this offline. There were some weirdnesses going on with the performance of the two efforts.
Okay, I was going to say that there is a, although lean check is strict, it's possible to make that lazy as well. And I think in one of the repos that you have, there is a lazy version that uses the same strategy as lean check. It would be interesting to include that as well and see how well that works.
Yeah.
The lazy version of lean check.
It's called lazy tiered small check, I think, or something like that, or tiered lazy small check. I mean, it's not a independent tool. It's just a module that implements the idea, but you can find it in there.
Thank you.
I had another observation as well, which was that when you were talking about the effect of size on time to failure, then the problem you found was to do with the size of the space that you draw keys from.
Yes.
Right, and certainly drawing keys from a very large space, especially if you draw them uniformly,
Yeah.
it's going to be very bad at falsifying many properties.
Yeah.
But that's a different measure for the size of the tree.
So at that, the actual experiment is about the sizes of the tree, but it would be harder to make the point in a slide. So I moved from the tree to a toy example that didn't really exist. So the keys is a different example, and the actual experiments are about the tree and its size, and the button and the performance is about also the tree size.
Okay, I've done some similar, or some experiments with the how to specify properties, and there you probably want the probability of a randomly chosen key being in a randomly chosen tree to be about 50%. And so there's a relationship that you want between the sizes of trees and the size of the space that you draw keys from.
Okay, I'm not really sure if I understand that. I'm going to ask you.
Let's talk about it.